April 2008, the world eagerly awaits the unveiling of a new engineering marvel. Amid much pomp and pageantry, the Singapore Flyer bursts into life. In the process, it dethrones the London Eye as the world's largest second-generation observation wheel. Its rim frame is stylishly slim, and from afar, the Singapore Flyer looks like a giant wheel standing on its own without any cable support. Just how did the engineers do it? Whether they are the products of modern engineering or monuments from the past, most major cities have unique icons to call their own. Now, the stage is set for one of the smallest countries in the world to begin construction of a mega structure on a scale never before seen. Singapore, an island city situated at the southern tip of the Asia continent. With an area covering only 700 square kilometers, it is populated by 4.6 million people. More often known for its economic prowess, Singapore now wants to position itself as a modern and fun city. Singapore has one big dream, a plan to build the tallest and largest observation wheel in the world, known as the Singapore Flyer. It will be an engineering phenomenon that people will talk about for years to come. An iconic design that will push the engineering limits of the 21st century. World-renowned Japanese architect Kisho Kurokawa is roped in to design the wheel. He has one philosophy for its design concept. He believes buildings are not just structures. They are living entities that can enrich human lives while retaining the natural order of the existing city.
So the idea only I can have for the Singapore Flyer is how I can create man-made nature. So this is the symbiosis of local identity and international technology.
The result? A wheel that stands 165 meters tall. This design marvel will be as high as a 42-story building. There will be 28 observation capsules, each capable of holding up to 28 people. The wheel will be surrounded by an irregularly shaped building. Considering that Singapore is well known as a food and shopper's paradise, it is no surprise that this terminal building will house restaurants and shops. As one of the new icons of the city, the Singapore Flyer is located where it matters. Situated at the confluence of Klang and Singapore rivers, the Singapore Flyer is visible from all angles around Marina Bay, the future city center. It is sited right across the bay from a future convention complex and casino, and as well as an international garden park. This site offers a commanding view of the city like no other.
It's almost impossible to imagine a postcard or photograph of Singapore not showing part or all of the Singapore Flyer within those sorts of photographs. And like the Opera House, the Eiffel Tower, and a variety of other iconic symbols in various cities around the world, the Singapore Flyer will most definitely fit comfortably into that impact generated by a man-made structure.
Engineers, professionals, and construction workers for the project hail from more than 10 countries. Brendan McNiven and his team at Arup are assigned the task of making the Singapore Flyer an engineering marvel. In order to do that, Brendan knows they have to move away from the conventional.
First generation wheels are like the original Ferris wheel, so you see them around a lot in theme parks and that sort of thing. Second generation wheel are like the London Eye. They're very, very large, and they have tension spokes in the form of cables going back to a central hub, and they also have motor-driven capsules around the outside.
In addition, second generation wheels make use of a triangular truss rim. This double-layered rim, held in place by tie cables, resembles a huge bicycle wheel with spokes. This method may be tried and tested, but to the naked eye, there is a lot of metal. As such, the biggest departure and undoubtedly the greatest breakthrough for the Singapore Flyer is the use of a rim frame that will be exceptionally slim and 30% lighter than the London Eye. Less metal makes the rim on the Singapore Flyer extremely flat. Imagine an ordinary ladder that is bent into a circle. But structurally, will it be as sound as a conventional wheel? General Manager of Technical Services, Phil Maddox, is pragmatic about it.
At the end of the day, it's a design. It's come off the drawing board with some tried and trusted technology, but inevitably there are always some small problems that need to be fixed on site.
One of the issues Phil and the engineers have to contend with is the fact that the main components are manufactured in different parts of the world and then shipped to Singapore. The spindle, capsules, and the main support legs are manufactured in Kobe, Japan. The cables that hold the legs and rim come from UK, while the main rim structure is manufactured in Malaysia. With the terminal building being built first, a gap is left opened to allow access for the arrival of the main components. This poses an additional difficulty as it restricts the space available for the construction of the Singapore Flyer.
And today, we are finally ready to start selection for the first supporting clamp here.
Project Director Kawamura is more than aware of the challenges he faces. In a simple sake pouring ceremony, he leads the rest of the team in praying for the work to go smoothly over the next 15 months. The first step is to erect the legs that will carry the weight of the entire wheel structure. The first section is lifted into place and bolted down. Eight more sections of each leg are subsequently added until they reach a height of 85 meters. The main legs are firmly held in position by 4 groups of support cables anchored to the ground. Each group has 6 support cables. Each specially manufactured support cable is 100 millimeters in diameter and weighs 8 tons. It has a braking capacity of 1,000 tons. To further minimize the movement of the legs, the engineers pre-tension each support cable to 200 tons. With the legs and cables in place, the spindle is the next component to be assembled. And tonight, the spindle arrives at the port. Transporting the spindle from the port to the site poses a great challenge. With 180 tons of pure steel sitting on a massive 15-axle configuration hydraulic trailer, it is difficult for this giant spindle to maneuver through the narrow streets of the older sections of the city. To minimize traffic congestion, the operation is carried out in the early hours of the morning. The 16-kilometer trip takes 3 long hours. Kawamura's next challenge is to lift the spindle and attach it onto the legs. This spindle will transfer the entire weight of the rim structure to its legs. Using cables, the wheel rim is then connected to the spindle. Finally, the capsules are fixed onto the rim. The erection method of the Singapore Flyer is significantly different from that of the London Eye.
The London Eye was a facelift method, so it was actually built out over the Thames and then lifted up horizontally. It's much easier to control the tensions in the cables when you do that because gravity is taken out of the equation.
The Singapore Flyer, on the other hand, has to be put together in an upright position. The wheel rim is bolted together segment by segment until it forms a circle. Engineers affectionately call this the vertical pie slice method. Now, the next step is to lift the spindle onto the main support legs. The entire lifting process is going to take a full day. The team has to make several stops along the way to check whether the position of the spindle is level or off-centered. It is an extremely tedious task, but it is vital that the engineers get it just right. "7 hours into the operation, and things begin to go wrong. The working platforms that have been attached at the bottom of the spindle are getting dangerously close to the legs. Any swaying or sudden gust of wind can cause them to crash into each other, and that can spell disaster. Kawamura decides to use chain blocks to readjust the platform manually. One of his workers is sent up to perform the brave task. The worker slowly adjusts the position of the platforms to retract them under the spindle, thereby reducing the protrusion from the sides. Finally, the spindle is safely lifted into position. Kawamura is able to complete the task without any more setbacks. But not for long. In December 2006, Singapore sees the highest rainfall recorded in 75 years, and this wet weather seriously hinders progress at the site. While work in Singapore may have slowed down, components being built in other parts of the world are forging ahead according to schedule. At the Mitsubishi manufacturing plant in Kobe, a prototype of the capsule has been manufactured. Engineers conduct various performance tests on it. While it may seem like a costly exercise, the prototype allows the engineers to deal with technical and design-related issues. Once the engineers are satisfied, production goes into full swing. Because the capsule design is unique to the Singapore Flyer, every one of the 28 capsules is assembled from scratch. Meanwhile, in neighboring Malaysia, the rim segments, the temporary vertical struts, as well as the capsule supports are being put together. The rim of the Singapore Flyer is actually a 56-sided polygon made up of 28 rim segments. Each segment comprises a main section that is straight. A smaller section is welded at an angle to each end of the straight section in order to simulate a curve. Pieced together, these 28 rim segments form a polygon that looks like a circular wheel when viewed from a distance. Engineers must make sure that the angles at which the sections are welded together are accurate. Otherwise, the rim will not fit properly together. Final adjustments to compensate for any variation in the curve is made in segment 28, the last segment. Once production is complete, the segments are loaded onto a barge headed for Singapore. Meanwhile, back in Singapore, the rain has finally stopped. Kawamura and his team now turn their attention to assembling the rim. Upon completion, the Singapore Flyer will be 165 meters tall. This is 30 meters higher than the London Eye. Observation wheels are getting larger with almost every new construction, and with the size comes an important consideration.
We've reached the point where having a traditional steel structure just becomes too big and heavy to build to that height. So the option of cables becomes the only way forward, really.
Reducing the amount of weight is the advantage cables will offer. These are fixed at one end to the spindle. They extend outwards to the wheel rim to hold it in position. On its own, each cable cannot support the rim. For this to happen, the 28 segments of the rim must be assembled together and the cables tensioned to act together as a single entity. With the Singapore Flyer being built using the vertical pie slice method, the dynamics are completely different from a wheel being built horizontally and then lifted into position. The engineering team has put together a computer program to calculate the lateral force at the bottom of the wheel. This is the point during construction where the force of the entire rim pushing downwards is the greatest. If the calculations are wrong, the partially constructed rim may collapse. And this is an engineering disaster the team must avoid at all costs. The engineers also come up with the idea of using 7 temporary vertical struts to hold the partially constructed rim firmly in place, one for every 4 rim segments. Though the struts are temporary supports, they are by no means makeshift assemblies. Putting up the temporary struts requires very meticulous and careful planning. Each strut is divided into 4 pieces. These are bolted together to form one sturdy arm. Building them this way ensures that removing them after the wheel is completed will be easier. The first of the 4 pieces goes up without any delay. This is firmly attached to the spindle. The second and third pieces follow shortly. But attaching the final piece is a complex and tricky matter. Because there is very little clearance between this final piece and the rim, it cannot be fitted from below like the others. This lowest and largest piece has to be lifted horizontally by cranes. As the top part of this piece comes into contact with the third piece, it is hinged at 2 ends. The engineers have to pivot this 4th piece into a vertical position. The plan works without a hitch. With a temporary strut in place, the rim segment can be fitted on. This is lifted onto the scaffolding and held in place by hydraulic jacks. The segments are bolted together. The cables are then attached. Each 4.5-ton cable is crisscrossed within the rim of the Singapore Flyer to give it more stiffness. With that, the engineers are able to do away with the need for a thick 3-dimensional rim structure, enabling a slim, elegant rim to be built. Once 4 rim segments are joined together, another temporary strut is put up. Braces are also fixed to hold the pie slice rim segment more firmly in place. Like the temporary struts, these are simply used to provide extra support. They will also be removed once the rim is fully assembled. Hydraulic jacks push the completed segments away from the working platform to make room for new segments. As the partially completed rim pierces into the sky, the effects of gravity begin to pose a challenge to the engineers. As more and more rim segments are put in place, the force exerted by the hydraulic jacks to hold and push the rim forward becomes greater and greater.
If we didn't have the force to push the wheel around, it just would have sat there half complete. The force enables us to keep pushing it around and rotating it to complete the whole wheel. We did a lot of calculations to work out what the maximum force is. The largest force occurs when you have half the wheel in place. The half wheel wants to actually swing around at the bottom, so there's a large lateral force at the building level to hold it in place.
Rim number 14, the reduction force is most big. That is over than 400 tons.
It is therefore a huge relief when the calculations prove to be correct. But the most challenging part of the rim assembly is yet to come. At the Mitsubishi plant in Kobe, the Singapore Flyer capsules are being manufactured, assembled, and vigorously tested. Phil makes a routine visit
Yeah, I'll be looking for build quality, quality of finish. I'll be more looking to highlight things that are going to be an ongoing issue. We're hoping to run this wheel for a long, long time, so if we can catch something now that saves us time later, of course, that'll be advantageous.
The capsules form an integral part of the Singapore Flyer, as they are the passenger-carrying component of the wheel. Indeed, their design has come a long way. Traditional wheels have open cars or bucket seats that are attached to the wheel structure by hinges, so when the wheel rotates, the seats are kept upright and level by the force of gravity. With second-generation observation wheels, the capsules are mounted on the outside of the rim. Each capsule of the Singapore Flyer is designed to comfortably take up to 28 people with the flexibility to move about within. Due to its weight and size, it is technically more feasible to fix the capsule supports in an inflexible arrangement to the rim. However, this poses a design challenge. If the capsule does not swivel or rotate as the wheel rotates, the people in the capsule will be standing on the roof of the capsule at the highest point of the wheel rotation. Engineers have an ingenious solution for this problem. Two giant gear rings are designed to form part of the capsule module. So, instead of attaching the capsule directly to the wheel, it is the gear rings that are permanently fixed onto the rim. The gear rings allow each capsule to rotate on its own axis as the giant wheel rotates. A stabilizer is fitted in each capsule to minimize any movements and provide maximum comfort.
The capsules are actively driven by a motor and gearbox arrangement, and we've made sure with the control system for floor stability that we maintain a stable floor throughout the ride.
Then there's the problem of humidity.
The climate in Singapore with such a high level of humidity always has the potential to give us problems with misting and condensation droplets forming on the inside and outside of the capsule glass. We have to be very careful how we channel air down through the capsules to be recycled without creating cold patches on the windows, which in turn will create moisture which will impair the view.
The design of the Singapore Flyer capsules is striking and unique. Aerodynamically shaped to reduce drag, it utilizes the latest composite materials to reduce bulk and weight. Learning from the experience of the London Eye, the capsules feature double-glazed laminated glass that allow fantastic views of the city in all directions without the problem of excessive distortion. A double-backed air conditioning system and a solid roof avert the problem of overheating on very hot days. Phil is pleased with what he sees.
As always, Mitsubishi are pretty impressive with their attention to detail and their mass production methods, and yeah, it's going well. I'm really quite happy with what we're looking at here.
Back on the ground in Singapore, Kawamura is also pleased that by working round the clock, his team is now ahead of schedule, and they are very near to closing the wheel rim. Little does he know he is soon going to face another tricky situation, and perhaps the greatest challenge that he will encounter on this project. At the construction site of the Singapore Flyer, rain has hindered the construction process. However, the extra hours put in by Project Director Kawamura and his team have ensured that the schedule is kept, and they are approaching the halfway mark to completing the Megawheel. The team now prepares to close the wheel rim. The immense weight exerted by the finished part of the rim bears down at the bottom, rendering the remaining gap too narrow for the last segment to fit in. Kawamura and his team have to widen this gap. The procedure using hydraulic jacks should be considered routine. After all, hydraulic jacks have been used very successfully to push the attached rim segments outwards to make way for new segments during the initial assembly. After endless days of long hours at the site, Kawamura is looking forward towards an early evening break. But this is not to be. As soon as the hydraulic jacks are set in motion, everyone at the site freezes. The popping sound does not augur well. Kawamura immediately orders work to be stopped and the jacks turned off. No one has the faintest idea what has just happened, yet. Engineers on site immediately inspect every inch of the wheel rim. They finally find out the cause. Whilst one side of the rim is being pushed back, the other moves sideways. One of the hydraulic jacks has slipped slightly, and the open ends of the rim are now misaligned. By using a drop line for measurement, the engineers find out that it is 8 millimeters out of alignment. For a piece of precision engineering, 8 millimeters is too much. Even if the gap is large enough to fit in the final rim segment, the ends will not meet, and the wheel rim cannot be closed. Kawamura must decide on the next course of action. He cannot release the hydraulic jacks for realignment as they are holding the entire rim in position. He explores his options with his engineers, but he is left with no other choice at this stage. He has to resort to pulling the two ends sideways manually to realign them. Chain blocks are attached to the open ends of the rim. As the hydraulic jacks widen the gap again, the ends are forced sideways into alignment. Low-tech as it may seem, Kawamura's plan works perfectly. The final pieces of the rim segments are slotted into place and are bolted down. This significant event marks the halfway point to the completion of the project, and the team celebrates. Now that the outer rim is closed, it is time for the engineers to concentrate on the next phase, tensioning the cables so that the temporary struts can be removed. A total of 112 cables hold the wheel rim in position and help to transfer the weight of the wheel to the legs.
It was a very detailed direction plan, and then it was just a matter of measuring the cable tensions in the wheel and measuring that against the physical position of the wheel. So we went back to the computers and did the modelling to actually check that all of the forces reflected what we saw down on site, and it was all okay. If it had differed in any way, then obviously that would have been a fair bit more work and a little bit more thinking to go and find out what had gone wrong.
A total of 112 cables hold the wheel rim in position. The cables are individually pulled downwards to the rim before they are tightened and bolted into place. But without proper calculations, it is impossible to know if each cable is correctly tensioned. So once all the cables are tightened, the engineers get ready to measure how tight they are. But this can only be done in the late evening when there is less sun. The technique used in the measurement involves laser lights. A laser machine shines a beam of light onto reflective bands that are on each cable. Deflections in the beams are then used to measure the vibration rates on the cables. These are recorded by an advanced computer program. Using these deflections, the program is able to calculate how tight each cable is. If there is any deviation from the set measurement, the tension on the cable is adjusted. The tensioning of cables runs smoothly. It is child's play when compared to the engineer's next task, and this requires more than just technology to get it right. Kawamura has been working on this project for the last 9 months, and today he is going to face what is potentially the most dangerous task yet. That is, the removal of the temporary vertical struts. These 7 struts have been built to provide the support for the rims during construction. Now that the cables are tensioned, they have to be removed. Just as they have been assembled, each individual strut has to be taken apart in sections. But there is a big challenge. With the rim segments and crisscrossed cables already in place, there is a lot less space for the engineers to maneuver around.
We have 112 cables, and that is a little difficult to take out. We have already tensioned, and adjusted. And the room to remove the strut is very narrow. Most narrow is just 4 inches.
With so little space to maneuver, the temporary struts cannot be removed like how they have been put up. Instead, 2 giant cranes are brought in and positioned on either side of the wheel structure. A temporary extension is built at the top of the 4th segment. Workers then detach this segment. The temporary extension allows the cranes to hold this segment once it is detached. These cranes then gently maneuver the segment out of position, laterally. There is a high possibility of entanglement here, and with the cables already tensioned, any snapping of a cable as a result of entanglement is a very dangerous situation, both to the workers on the ground as well as to the wheel structure. Therefore, the team takes extra care and moves very slowly. With the cables converging at the spindle in the middle and the clearance becoming smaller, it gets increasingly difficult to remove the struts. Fortunately, work progresses without any accidents. Meanwhile, the braces are also removed. Over the weeks, as more temporary struts and braces are removed, the image of a trim and refined wheel structure begins to appear. For now, all is going according to plan. In Kurokawa's original proposal for Symbiosis, the Singapore Flyer is to be built within an irregularly shaped terminal building. Although the building structure has been constructed before the wheel, certain allowances have been made.
In order to build the wheel the way we did, we had to leave part of the building open to allow access for the contractor's heavy equipment needed in building the wheel rim and the passenger decks. This was planned from the start. Now we're moving towards the end of the project. The civil works contractor wants to get on and complete his building, so he's on the case.
Other than closing the terminal building, the building contractors also have to erect the passenger platform. With a driving motor, and more importantly, the capsules still to install, a compromise has to be reached between the 2 sides on how work should progress henceforth.
So this time very important to share the work with the building construction site. And then after we removed all the temporary structures, we cannot work on the courtyard. So we'll start fitting the cabins on the roof of the opposite side of the building.
Now that the wheel is in position, how does it turn? Contrary to popular belief, the spindle does not turn the wheel. It merely supports the weight of the wheel. Instead, tires driven by motors are attached at the base of the wheel rim to turn it. These have to be put in place before the capsules can be attached. Just like the spindle, the first batch of passenger capsules arrives at the port from Kobe, and once again, they can only be transferred to the site at night when the roads are less busy. With the experience gained from transporting the spindle, moving these capsules does not pose any problem for the team. And tomorrow marks a significant milestone for the construction of the Singapore Flyer. The construction of the Singapore Flyer has reached the halfway mark. As the temporary struts and braces are removed, the image of a slim and refined wheel starts to appear. And today is a big day for the crew. The first capsule is going to be attached onto the wheel rim. It marks the beginning of the end of a long construction process for the team, but they are taking absolutely no chances at all. The morning starts off with everyone praying for good weather in the days to come. Even though the crew come from various parts of the world, there is respect for everyone's cultures and rituals. Now that the gods are appeased, the first capsule is lifted onto a platform on top of the terminal building. Work is carried out on the roof so that the terminal building can be closed and construction of the boarding platform can proceed without hindrance. The waiting crew slides the capsule carefully into position and bolts it down. Once it is secured, the next capsule is then attached. But before that, the wheel has to be rotated 180 degrees so that it can be fitted directly opposite the first one. Installing the capsules sequentially will result in uneven weight being loaded onto the rim, thereby adding unnecessary lopsided stresses to the cables. By installing the capsules on opposite sides, the wheel remains balanced. One by one, the capsules take their place on the wheel. And now, the final physical appearance of the Singapore Flyer is revealed to the world for the first time. With the end drawing near for the construction crew, another team of personnel stands by to begin a new phase, the testing of the Singapore Flyer. Singapore is very close to the equator, and it is generally hot all year round. But when it rains, it pours. And their experience with all the rain has taught the project engineers that the weather condition in Singapore is going to be a constant challenge they have to face. Other than the heavy downpours, the country experiences what is known as Sumatra squalls between May and October each year.
In Singapore, the Sumatra squall winds can actually rise very quickly, so it can be dead calm 1 minute and then 10 minutes later it can actually be very strong winds. There will be a case perhaps where you're up at the top of the structure, one of these high wind squalls comes out of nowhere and you'll feel a little bit of movement.
To minimize vibration of the wheel, mass dampers are installed in the support legs. But without actual testing, it is impossible to know whether the mass dampers will actually work as planned. In order to analyze how prone the Singapore Flyer is to wind vibrations, the engineers have to simulate a scenario of an actual squall. A simple yet ingenious plan is put into action to replicate the wind vibrations. 20 men are sent up the hollows of the two main support legs, 10 in each. The space is so narrow that even the camera crew cannot fit in. The team is now ready to play. Follow the leader with the guy on the ground. 20 men jump in unison to the instruction of their commander. This is to prevent the vibrations from canceling each other out if their movements are random. The movement is recorded and analyzed. After putting the numbers through a computer program, the team is satisfied. The movements are strong enough to be felt, but not big enough to cause any problems. The team is now ready to move on to another major test to find out if the wheel will cope with a full load of passengers. With a total of 28 capsules, the Singapore Flyer is designed to handle 784 passengers at full capacity. But this has never been tested out, till now. The test is deceptively simple. Even though it looks seemingly primitive compared to our high-tech engineering marvel, it is brilliant. By using 3 canisters of water, which is equivalent to 75 kilograms to represent a human being, our engineers have found the most accurate way to push the wheel to its limits. Unfortunately, the canisters ordered do not come filled. It looks like our water boy here is going to have to work overtime today. A total of 2,520 canisters are filled and taken aboard the capsules. Each capsule carries 90 canisters of water, simulating 2,250 kilograms of human weight. The team watches on as the very last canister goes aboard the capsule. And the wheel holds. While there is never any doubt that the Singapore Flyer can take the loading, the test confirms it for the team. With all the tests conducted, there remains just one more process before the Singapore Flyer can be opened to the public. Kawamura and his team of engineers may have looked into all aspects that can go wrong technically. However, there is still one aspect that they cannot control: humans. How well the Singapore Flyer can be managed depends on how well the day-to-day staff is trained. Although operating the Singapore Flyer is not exactly rocket science, dealing with any operational problems calmly will require a certain amount of nerve. The trainees undergo strict training and are asked to experience for themselves the scenario when the stability control in a capsule is lost. The trainees are transported to the top of the wheel. There, an engineer on the ground releases the catch to the stability control in a capsule. It begins to sway. Picture this scenario: 28 passengers trapped in an enclosed space at a height of 165 meters above ground level. With a loss of stability, this experience can be pretty harrowing. With all preparations in place, there remains only one logical thing to do: open the Megawheel to the public. The day finally arrives. It has taken 1.5 years for the Singapore Flyer to take shape. Today, the world eagerly awaits the unveiling of a new engineering marvel, the Singapore Flyer. It is 30 meters taller than the London Eye, yet it is 30% lighter. Observation wheels have come a long way since George Ferris erected the first one in Chicago in 1893. Standing at 80 meters, it is taller than any other skyscrapers at that time. It is named the Ferris wheel after its creator. More than 100 years later, a breakthrough in observation wheel design created the first second-generation wheel. The London Eye uses fully enclosed capsules that have a motorized stability system to turn the capsules in synchronization with the rim rotation. This innovation allows the capsules to be placed on the outside of the rim, thereby providing unobstructed views. Standing at 135 meters, the London Eye is the largest observation wheel at the time of its official opening in early 2000. In 2006, the star of Nanchang in China's Jiangxi province surpassed that height to reach 160 meters. However, because it has been built as a traditional Ferris wheel with swivel buckets, few people outside China took notice. 2 years on, the world's attention is now focused on a slim and elegant new marvel, the Singapore Flyer. The grounds of the new attraction take on a festive mood.
The Singapore Flyer is clearly the first of its kind, and it is the largest observation wheel in the world, and it is here in Singapore in an absolutely outstanding location, which will really transform the skyline of the city.
In the presence of over 1,000 invited guests, the guest of honor, Prime Minister Lee Hsien Loong, officiates the Singapore Flyer's opening.
1, 2, 3!
Accompanied by a dazzling laser and fireworks display, the Singapore Flyer is launched, and a new icon is born. The night lights of the Singapore skyline from the Singapore Flyer are breathtaking. And on a clear day, you can peer into the horizon to see as far away as Indonesia and Malaysia. Nestled in the center of exciting future developments, the Singapore Flyer is indeed the focal point of activities. The Singapore Flyer is more than an engineering marvel. It is an experience to relish. Perhaps Kurokawa sums it up best.
Singapore is a very small country and very flat. So the people don't have any view from the high points. Of course, they have high-rise buildings. On top of the high-rise buildings, they can just understand what is the Singapore is. But such a movement of the flyer, they're gradually coming up to the top and then coming down, makes a different experience.